Good morning, everyone. I am Zhimin Hu from Peking University. My paper is D-Gates Theme-Based Gates Prediction in Dynamic Themes. This is my presentation outline. I will introduce the research background, related work, D-Gates model, limitations, and future work. Recently, eye tracking technology has gained importance in many different fields. It can be applied to neuroscience and psychology, industrial engineering, marketing and advertising, computer science, and so on. For example, it can be applied to marketing strategy analysis, cognitive research, medical education, gaze-based interaction, collaborative system, and gaze-contingent eyeglasses. In the field of virtual reality, eye tracking technology can be applied to gaze-contingent rendering, redirected working, and gaze behavior analysis. However, currently, the most common solution for eye tracking in VR is a hardware-based solution which requires a device called an eye tracker. Eye tracker is accurate, but is currently expensive, not widely available, may need calibration, and it cannot predict future gaze position. Considering the limitations of eye trackers, we desire to propose a software-based eye tracking solution in VR that only employs information from the VR system. This means our solution does not utilize eye trackers. Specifically, our goals are analyze users' gaze behaviors in virtual reality and predict users' gaze positions based on the characteristics of users' gaze. Our research is related to the work of ceiling object detection. Ceiling object detection aims at detecting ceiling objects from images. The top are the original images and the bottom are the ceiling objects. Another important work is ceiling prediction. Ceiling prediction predicts the ceiling maps of original images. The left are the original images and the right are the ceiling maps. Recently, with advances in deep learning, many deep learning-based ceiling predictors have been proposed and have achieved good performance. Ceiling's attentive model, namely the SAM model, is one of the best ceiling predictors. In the field of virtual reality, the ceilings in 360-degree images have also been explored. The ceilings in 360-degree videos has also been studied by researchers. In our previous work, we explore the gaze prediction in static virtual scenes. Compared with previous work, we desire to predict 2D gaze positions rather than detect ceiling objects or predict ceiling maps. Furthermore, we focus on 3D virtual scenes instead of images or videos. We desire to explore dynamic scenes instead of static scenes. This is our contributions. We propose a novel CM-based gaze prediction model called D-Gaze. We provide comprehensive analysis of human gaze behaviors in dynamic virtual scenes. We built an eye-tracking dataset that contains 43 users' gaze data in 5 dynamic scenes. Our workflow includes data collection, gaze behavior analysis, Selenium-based gaze prediction model, and model evaluation. In the data collection process, totally 43 users participated in our experiments. They are asked to explore 5 dynamic virtual scenes. Specifically, we place some animals in the scenes and utilize the animals as dynamic objects. We employ HTC Vive and an eye tracker to collect the user's exploration data. During the experiments, users are asked to freely explore the scenes and they are given no task. We collect the scene screenshots, users' gaze positions, their head poses, and dynamic object positions for analysis. This video shows our experiment environment and the data collection process. We first analyze the distribution of users' gaze positions, and we find that most of the gaze data lies in the central region of the screen. We employ Spearman's rank correlation coefficient to assess the correlation between gaze positions and object positions. We find that users' gaze positions are strongly correlated with dynamic object positions. The correlations between gaze positions and object positions at different time intervals are also explored. The results show that both real-time and past object positions are correlated with gaze positions. We also calculate the correlations between gaze positions and head velocities at different time intervals. We discover that both real-time and past head velocities are correlated with gaze positions. We also analyze the distributions of gaze positions on setting regions of the VR image. We find that most of the gaze positions lie in the most setting region of the VR content. Based on our analysis, we propose a CNN-based gaze prediction model called DGaze. DGaze consists of 3 modules: Sequence encoder module, sequence encoder module, and gaze prediction module. The sequence encoder module utilizes SMResNet to extract the sequence features from the VR content and then encode the sequence features. Sequence encoder module employs an 1D layer to encode the object position sequence and head velocity sequence. The gaze prediction module combines the outputs of the sequence encoder module and the sequence encoder module to predict the gaze positions. By setting the gaze positions at different prediction times as our targets, DGaze model can be trained to predict not only real-time gaze positions but also future gaze positions. Generally, DGaze is used to predict gaze positions without the help of eye trackers. However, if an eye tracker is available, we can also encode the gaze position sequence in the sequence encoder module to predict future gaze positions with higher precision. In this case, we call our model DGaze_ET, which means eye tracking data is utilized. We analyze our model's real-time prediction performance on both a dynamic dataset and a static dataset. We find that DGAze performs best in both dynamic and static scenes. The CDF curve of the prediction errors are also calculated. The higher the CDF curve, the better the performance. We find that DGAze performs best in terms of CDF curve. We also calculate DGAze and DGAze underscore ET's prediction performance in different prediction times. The lower the prediction error, the better the performance. The results show that DGAze and DGAze underscore ET outperform other methods in different prediction times. This video shows DGAze real-time prediction performance. The green cross refers to the ground truth and the red cross refers to DGAze. The blue cross refers to other method. This video shows that in practice, DGAze performs better than prior method. We apply DGAze to gaze contingent rendering and conduct a user study to evaluate its performance. The results show that DGAze performs significantly better than prior method. This video shows the application of gaze contingent rendering. We also apply DGAze to a task-oriented game. This video shows DGAze performance in a game scene. The results validate that DGAze still performs better than prior method in a task-oriented game. Our model has some limitations. First, our dataset is restricted to free viewing conditions. Task-oriented conditions are not explored. In addition, we only utilize moving animals as our dynamic objects in the data collection process. Finally, the influence of sound is not considered in our model. There are many avenues for future work. First, we should overcome the limitations of our model. Second, we can improve our model's performance by fine-tuning the parameters. In addition, we can extend our model to consider more input features. Finally, we can convert our model to other systems like AR and MR systems. This is the end of my presentation. Thank you for your attention.